on the calculation of the effective area for different cases. So, example 3.9. So in example 3.9, you have an angle that is connected by weld, okay? Longitudinal and transverse welds. So we're going to see how to solve this problem. So in example 9.3, you're required to compute the ASD, allowable tensile strength of the shown angle the angle is 8 by 6 by 3/4 of an inch, and it is welded on the end. So that's a transverse weld. And on the sides, so that's longitudinal weld. Of the 8-inch leg. So it's only welded on the 8-inch leg. The 6-inch leg is free. And you're given the properties of the steel used. F yield is 50 KSI. And the ultimate stress for the steel used is 70 KSI. So how does this section look like in the connection? So you have an angle. And this angle is 6-inch by 8-inch, and the thickness is 3/4. And this is connected to a plate on the 8-inch leg. So you have a plate here, and then it's connected, okay, by longitudinal and transverse weld. So if this is a front view, so a top view will look like this. The side view actually first. So for the side view, you have this angle, and then you have the plate here, and there is a tensile force applied. Okay, there is a tensile force that gets transferred from the angle to the plate. Okay, and it's connected. This 8-inch leg is connected. What's the problem here? So this is the angle here. And it's connected to a plate. So this is the front view. This is side view, and this is top. So here it says that it's connected by longitudinal weld on the side here. So that's something that you're going to see over here. So that's the weld, okay, on the side, on both sides here. So that's the longitudinal weld. And you have a transverse weld as well. that's going to be something that you actually see here. Okay, so that's the transverse wall. Okay, and you're required to find the strength that using the ASD design method. So you're given the properties of the steel. The F yield is 50 KSI. The ultimate stress is 70 KSI. You don't need to get it from the table. Okay. And then now you just have to see the strength regarding yielding of this section and the strength for the fracture of this section. Okay. What properties would you need to do that? What are the properties needed? So this is your angle. So that's the 6-inch leg. That's the 8-inch leg. For calculating the shear lag factor, you're going to need this distance, X bar, okay? Or Y bar, we're going to see which distance on the table is going to be called. But in the cases for the shear lag factor, it's always called X bar, okay? So you need the area gross, right? And you need X bar. So from the tables, so which table, just look for which table. So we're looking for angles. Angles are in table 1.7. We're looking for L6, sorry, 8 by 6. So that's 8 here. On page 142, you have L 8 by 8 and then 8 by 6. So if I zoom out a little bit, so you have here the L 8 by 6 by 1 inch and then 7 by 8, and then 3/4. That's what we have, okay? The 3/4. So you're looking for the area gross. So area gross is 9.99 inch square, okay? And then we're looking for the X bar, okay? So is it an X bar distance or a Y bar distance? So just look at this figure here. You're looking for the distance, the centroid, in the long leg or the short leg? The short leg, okay? So actually this distance is the horizontal distance X bar over here, okay? So we're looking for X bar, so X bar is given here on this side, so that's X bar here, okay? And its value is 0.9, no. How much? Yes, 1.56. Okay, I was going for the 8 by 4 by 1. No, yeah, 8 by 6, so it's 1.56 here. Okay, the 1.56. So so that's table 1.7 on page 142. So table 1.7, page 142, the area gross is equal to 9.99 inch square, and X bar is the 1.56 inch. Okay, that's what you require from those tables. And then we're going to check yielding and fracture for the section. Okay, so for the yielding of the gross section, P nominal is equal to the area gross multiplied by the F yield. So the area gross is the 9.99 inch square, and the yield stress is the 50 KSI. So this section can withstand a load of 499.5 kips without yielding, okay? But you just need to apply a factor of safety to get the allowable stress, okay? So for the LRF, for the ASD, the allowable strength of the member will be the nominal strength divided by the factor of safety, omega. So the 499.5 K divided by the factor of safety, how much is the factor of safety? In this case, it's 1.67. So that's going to be 299.1 kips. So that's the maximum or the ultimate or the allowable load, okay? The load is not expected to be more than this, including this factor of safety. And then you should check for the fracture of the critical section. So when calculating the fracture of the critical section, you need the net area, okay? So how much is the net area? The net area is the area gross minus the holes, right? How many holes do you have here?
0.
No holes, so the area net is equal to the area gross. Here, I just have a note for you, okay? If you have weld, okay, so when you have a weld like this, so let's say you have a member, an angle like this, and it's connected by weld at the end here, okay, some weld here, okay, like the case that we have here. Does this necessarily means that the area net is equal to the area gross? If you don't have any information other than this information, okay, just how it's connected, so it's connected by weld, that means that the area gross is equal to the area net. But sometimes it's connected by weld to the ends, but it has holes here, not to transfer the load to connecting element, but actually to get connected to, let's say, an angle here. Okay? So even though there is no bolts at the end, but it might be connected to another member or transverse member by bolts, okay? And in this case, when you take the area net, you have to make sure that you include those bolts here. Okay? Yes?
Those bolts, is there like a set distance or something? If they include those, or do we have, like along the length?
You have, like, let's say you have this member, okay? It's connected here by weld, it's connected here by weld, and there is a transverse member connected to it, okay? This transverse member is connected here by bolts. So the bolts here are not transferring any of the longitude or any of the tensile load. They are just used to connect this member to the transverse member, okay? So although the bolts are not part of the connection of the element, okay, but they are actually a hole in the member, right? So there is no distance for them. It depends on the location of the other member. But anyway, we won't have this case in our course, but this is something for you to keep in mind, that even if the connections are weld, okay, you have to make sure, like if you're designing an entire structure, so you have to check that there is no bolts in the entire member, not only at the connection. So now the area net is equal to the area gross because we don't have holes or bolts. And then we need to calculate the effective area. The effective area is just the multiplication of the net area by the factor, the shear lag factor U. So how to calculate the shear lag factor U, okay? So U, the shear lag factor, So the question here, are all the elements of the member connected by welds or bolts? What are the elements of the member? You have an angle. What are the elements of that angle? The two legs. Are the two legs connected or effective in transferring the longitudinal load? No, only one leg is effective. That means that when you go to table D31, okay? So table D31, it's not case 1 because the tensile load is not transferred through all the elements. So it's case 2 here, okay? So U is equal to 1 minus X bar over L, okay? Does case 8 apply? No, case 8 applies if the angle, or you have an angle or a double angle and they are connected by fasteners or bolts, okay? Which is not the case here. So here we just have case 2. Case 2 is the only case that is applicable to our problem here. So U is equal to 1 minus X bar over L. So per case 2, in table D31, okay, U is equal to 1 minus X bar over L. Okay? So how much is X bar and how much is L? X bar, we extracted this value from the table, it's 1.56 inches. And how much is L? Okay, I didn't give you how much is L, but it's given in the problem. So this weld is 6 inches long. So that's L, okay? This distance is L, the length of the connection. So divided by the 6 inches. So U is equal to 0.74. Okay? So now we can go ahead and calculate the effective area. So the effective area is U multiplied by the area net. So U is 0.74 multiplied by the net area, which is 9.99 inches square. So that's equal to 7.39 inches square. So here, as you see, U is equal to 0.74 of the area net, and the area net was equal to the area gross, okay? So the effective area is 0.74 of the gross area, okay? So if you use the tables in section, I guess, 5, okay? The values that you get from the table will be higher than what you get from the equation here. The difference is from 0.74 to 0.75, okay? So you're gonna have a slight difference, but you need to find this value, right? Because 0.75 will give you like a more load, and you actually need to have the lowest load, right? So now the effective area is 7.39 inches square. So the nominal strength regarding the fracture of the critical section is the effective area multiplied by the ultimate stress of the steel. So it's 7.39 inches multiplied by the 70 KSI. So that's a total of 517.3 K. So for the ASD, this nominal strength is just divided by the factor of safety omega, which is equal to 2. So 517.3 divided by 2. So that's 258.6 K. So now we have two values, 299.1 for the yielding and 258.6 for the fracture of the critical section. So which one governs? the fracture. So that's the governing value. Or governing strength. Any questions? Okay. So
I had a question.
Yep.
So we're checking to see if yielding or rupturing governs the load case, right? Will the values in the table, even though they don't necessarily match exactly, will they always show which load case governs?
in most cases, because the value, like the value that you have for in the tables, the value that you have for the yielding is correct,
Right.
okay? Because there is no approximations in the yielding. While for the fracture, it's based on the 0.75 value, and usually it's the difference won't be that large, okay? So in most cases, yes. So now we're gonna have a provision in the AISC regarding the connecting members. So for the connecting members, or the connecting elements, what do we mean by connecting elements? Those are things like splice plates, splices, okay, where you have to connect two members and gusset plates, for example. So this is not the element itself, or not the member itself. We're not talking about the member that is, holding the tensile force. We're talking about the connection plate, either splice plate or a gusset plate. So the AISC specifies that the net area, when you calculate the net area of this connecting plate, okay, the net area cannot be larger than 0.85 the gross area of the plate. Or not the member. So for example, let's say you have a W shape like this, and you're connecting it to another W shape by plates like this. So that's what we mean by this part, or by this statement. When you're connecting those plates, okay, so those plates are actually transferring the tensile load from one member to another, okay? So they are just not, they are not a member, they are just a connection, okay? They are connecting plates, transferring the load, the tensile load from one member to another, okay? Splice plates or gusset plates. So when you design those gusset plates for a tensile force, okay, the splice plates, the area net cannot be larger than 0.85 of the gross area, okay? So let's see an example here on this provision. So example 310. So in example 310, it states that the tension member you have F yield given of 50 ksi, and the ultimate strength is 65 ksi. So it says the tension member of example 3.6 that we solved earlier is assumed to be connected at its ends with two 3 by 12 inch plates. You are required to determine the LRFD design tensile force that the two plates can transfer. So in example 3.6, you had an angle, sorry, you had a W shape like this, okay? It was W 10 by 45, okay? And now it says that this member having a tensile load like this, okay, is connected by two plates like this. Those plates, each of them is 3/8 of an inch by 12 inch wide, okay? And they are connected by 3 bolts like this, okay? So for a side view, you have the W shape like this. And you have the plates on top. The plates are 8 inches wide. So the width of the plate is 12 inches. And its thickness is 3/8 of an inch. And they are connected by bolts to the flange of the W 10 by 45, okay? And you're required to find how much can those plates, how much load or tensile load can those plates transfer, okay? So it's a tensile member or a tensile element, okay? So we're gonna follow the exact same steps, but the only thing that differs here is this part of the specifications, that the area net cannot be larger than 0.85 of the area gross. So even if it's larger, you're gonna just use 0.85 of the area gross. So you're gonna calculate the area net. If it's less than 0.85 of the gross area, that's fine. If it's larger, you're gonna use the 0.85 of the gross area. That's all, okay? So there is nothing complicated here, just that check. So for the solution here, you need to check the two things, the yielding of the cross section and the fracture of the critical section. So for the yielding of the cross section, the nominal load is equal to the area cross multiplied by the yield stress. The gross area, okay? How much is the gross area? The gross area is, how much is the gross area of the plate?
3/8 times 12 inches. 3/8 times 12 inches.
Yes. 3/8 multiplied by 12, okay? So that's the gross area multiplied by the yield stress, which is 50, okay? And then for the LRFD, the ultimate strength is just phi multiplied by Pn. So phi is 0.9 multiplied by Pn. So 0.9 multiplied by 3/8 of the inch multiplied by the 12 inches multiplied by the 50 KSI. So the total is 405 kips. So that's the maximum or the strength of those plates. Okay. Sorry, there is something that we missed here, where you're connecting two plates. So you have to multiply by 2 here, because you have 2 plates, 1 plate on top. So this 2 is for 2 plates. Okay, you have 2 plates, 1 on top and 1 on bottom. So this is the strength for the yielding. So what about the fracture? Of the critical section. So how much is the area net, the net area of the 2 plates? You have two plates multiplied by, so the net area is the gross area minus the area of the holes, right? So it's 2 because we have 2 plates. The gross area is the 3/8, 3/8 of the inch multiplied by 12. So that's the gross area. And then the holes. How many holes do you have in each plate? When it breaks, when this plate breaks, 2 holes in each plate. 1 hole here, 1 hole here, and the same for the plate that is on the bottom. Okay? Any question? Is it not clear for anyone? So you have 2 holes in each plate. Okay? So it's given in example 3.6. So 2 multiplied by the bolt size is 3/4 of an inch from problem 3.6, okay? Plus 1/8 of the inch for the clearance multiplied by the thickness of the plate, which is 3/8 of the inch. So the total net area is 7.69 inch square. So now comes the check, okay? This is the only new thing in this problem, okay? That you have to check that this area net is higher or greater than 0.85 of the gross area. So how much is 0.85 of the gross area? It's 0.85 multiplied by the area gross of the 2 plates. So it's 2 multiplied by 3/8 of an inch multiplied by the 12 inch. So this is 7.65 inch square. So actually your actual net area is 7.69 inches square, but 0.85 of the area gross is smaller than this value. It's 7.65. So actually when you design those plates for fracture, you're going to use the 0.85 area gross. That's what the AISC states. The area net cannot be larger than 0.85 of the area gross, okay? So if it's larger, like the case that we have here, we're going to use the 0.85 of the area gross. So we're going to take the area net equal to the 7.65 inch square. This is only for the connecting plates or connecting members. And of course, U is equal to 1, right? Just have plates, okay? You have this is a plate, right? So the load is transferred through the entire member, okay? And you don't have well. If you have longitudinal well, then there is case 4 that applies. But here, U is just going to be 1, okay? So the ultimate load is phi multiplied by the nominal load, and phi, the nominal load is the area, the effective area multiplied by the ultimate stress. So phi is 0.75, the effective area is U, which is 1, multiplied by the net area, which is 7.65, multiplied by the ultimate stress, which is 65 ksi. So the total strength of the two plates is 372.9 K. So which one applies here? So for yielding it was 405. For fracture it's 372. So the 372. So fracture governs. Any question? Any questions so far? Okay, great. So